trivial character of Z mod M star that the value of the Dirichlet L function in 1 was non-zero. And he had a pretty easy proof of this. Easy if chi is not equal to chi bar, but when chi is equal to chi bar, which is equivalent to the fact that chi squared is the identity, chi is a quadratic character because chi bar is the same as chi inverse. Then he had a proof that involved the relates L chi S to the arithmetic of quadratic field, which was either plus or minus F. So I'm going to try to show you that today. And to do that, we'll jump ahead of Dirichlet a little bit. We'll come back to him. But we'll jump ahead to the work of Benedict, who's a student of Dirichlet, who defined the zeta function of a general number field, generalizing the Riemann zeta function, zeta function of number fields. So there were two generalizations of the Riemann zeta function. I mean, the most naive is, so as I said, we had the zeta function S, which actually was due to Euler. So Dirichlet made the generalization to L chi S, where he put in a character, but he still summed over the integers. Prime of M, chi of n to the S. So that's a rather simple generalization. And then there's the generalization of Benedict, where we get the zeta function of a number field, S, and we'll define that today. And this is the zeta function of the rational numbers. Okay, so to do this, I have to do a real quick course on number fields, or at least say what I need about them to define the zeta function, and then we'll compute them in a few cases and see when they're related to Dirichlet algebra. So assuming people have a little bit of the theory of number fields. So a number field is by definition a field which has finite degree, finite dimension, as a rational vector space, say n, the degree of the number field, over the rational numbers. And you can get such a number field, for example, by taking an irreducible polynomial of degree n and adjoining a root. So f of x is in q of x. It's a mnemonic polynomial x to the n plus a1, x to the n minus 1, etc. But this is irreducible. Then you can get such a number field by adjoining a root, which is the same as the field Kronecker would have written it like this: q of x modulo the maximal ideal generated by this irreducible polynomial f. So for polynomials in one variable, the theory of number fields is obtained by joining its roots. And in fact, every number field can be generated by one element. So it's a rational vector space. It looks like q plus q alpha plus q alpha squared. Anyway, the basis of it is the powers of alpha up to n minus 1, and then of course alpha to the n can be written in terms of those using this polynomial and the fact that alpha is a root of it. Okay, so that was the beginning. Now, inside of the rational numbers are interesting as a field, but much more interesting is the ring of integers. And every number field has such a ring, a canonical such ring in it that contains the integers, called the algebraic integers. Okay, so that's a subtle construction that Benedict found that is the reason we have the theory of modules today. So the algebraic integers are by definition the elements alpha and k that satisfy a mnemonic integral polynomial. That's what an algebraic integer is. It satisfies a polynomial, which is monic, where all the coefficients are not just rational numbers, but integers. And what's not immediately clear, and what Benedict had to develop the theory of modules to do, was that this is closed under addition and multiplication. This is a ring. Closed under addition and multiplication. If you think of that, you know, if you've ever tried, you know, and here's some obvious algebraic integers. There's the square root of 2 and the square root of 3. One satisfies the polynomial x squared minus 2. This one satisfies x squared minus 3. So imagine you had a number field that contained the square root of 2 and the square root of 3. Why is the sum of the square root of 2 plus the square root of 3 an algebraic integer? Not so obvious. So that's why the theory of modules is developed to prove that this is a closed end. And one also knows that it is as a module over the integers, it's a free module of rank n. So in other words, you can write it, you can find n different algebraic integers so that every algebraic integer is spanned by those over the integers. You can't always find an algebraic integer such that the basis for the algebraic integers is the power of that integer. So note, A may not have the form, I'll give you an example of this as we go along, Z of alpha. But it always will contain such a subring of finite index. Namely, if you take any generator of the field K, so any solution of an irreducible polynomial of degree n that generates K, and you take a sufficient integral multiple of it, the coefficients of the polynomial eventually become integral, and then alpha becomes an algebraic integer for which these powers are independent. So that generates a submodule of the full ring of algebraic integers of the same rank, so it has to be a finite index. So you can always at least find something a finite index where it's just powers of alpha, but in general you have to take different elements that give you a basis. We'll do some examples, I promise. Okay, good. Now, it follows, once you know that A has this structure over the integers, that every ideal I, which is not equal to 0 in A, has finite index. And that index is an invariant of the ideals, a positive integer, and that index we'll call the norm of I. And the reason you call it the norm of I is for the simplest ideals, which are just multiples of some fixed algebraic integer. If I is equal to alpha times A, or multiples of alpha, then the norm of I is the absolute value of the norm of alpha, where the norm of alpha is the constant coefficient of the characteristic polynomial of alpha. So this is a generalization. Not every ideal has this form. That was one of the big discoveries of the 19th century. That was Kummer's discovery, that you could have ideals that were not generated by one element. But if it is generated by one element, its index is just the absolute value of the norm, and so you call the index the norm of the ideal in general. And now I can tell you what the zeta function is. The zeta function is just given as the sum over all ideals of the ring of integers, which are non-zero, of 1 over the norm of the ideal to the s power. And that's a generalization of this, because in this case, A is equal to the integers. Every ideal in this case happens to be principal, right? And the norm of I is just the absolute value of n. So I'm just summing over the positive integers, etc. Okay? If you did the Gaussian integers, if you had k to be q of I, and then the ring of integers is known to be z plus z of I, and in this case, Gauss proved there was a Euclidean algorithm, so every ideal is principal. It has 4 possible generators, this and powers of I times it. So the zeta function of the norm of I, the index of this ideal, is the norm of this element, absolute value, which is just a squared plus b squared. And so the zeta function of Q of I would be 1/4 the sum over all pairs A and B, which are non-zero, 1 over A squared plus B squared to the S power. And one proves, and if you look at this, this is in some sense more complicated because you have to know what the ring of integers and its ideals are. On the other sense, it's simpler because the coefficients of this Dirichlet series, if I wrote it out as Bn n to the minus s, these coefficients Bn are just the number of ideals of index n, right? And so Bn, number of I of index n in A, and that's a number which is greater than or equal to 0, where the coefficients here are complex numbers of absolute value 1, but they could be plus and minus and all kinds of things. Okay, now the number of ideals of a given index is finite because the number of subgroups of this of a given index is finite. And ideals are special types of subgroups that are closed under multiplication from the grid. So that already shows that these numbers are finite, but they're non-negative, and so you might expect that this series grows as s tends to 1, even though this has a special value, and in fact this always has a pole at s equal 1, and but it converges for the real part of s greater than 1, just like the zeta function. So in that sense, it's quite close to the zeta function. Okay. So that's the definition. Now, you don't get very far with that definition because no one knows how to compute the number of ideals and that kind of thing. So you need something like the Euler product. And a big theorem of Dedekind is that every ideal factors uniquely as the product of prime ideals. By ideal, I always mean non-zero ideal. I don't want to keep saying non-zero ideal. Prime ideals. So that namely, the ring of integers is what's called the Dedekind domain. An ideal can be written as P1, A1, PR, AR, and these primes and the powers are uniquely determined by I. So what's a prime ideal? Well, a prime ideal in the ring of integers is just one where the residue ring is an integral domain. But since we've seen that all ideals have finite index, the reason an ideal which is non-zero has finite index is the ideal contains some non-zero element, and alpha times A is a finite index in A. So I is a finite index. So this quotient A mod P is a finite integral domain. That's what a prime ideal does. But a finite integral domain is a field, so it's also a maximal ideal. So that's the definition of a prime ideal. The ideal's in A, where the quotient is a finite field. In general, the quotient by a general ideal is a finite ring. Okay, now finite fields have a characteristic, and finite fields of characteristic P. And so any prime ideal, multiplication by P in this quotient has to be 0, which means P has to be contained in this ideal. So the prime ideals of characteristic P are exactly the maximal ideals containing PA. All right? Or equivalently, they're the maximal ideals in the finite ring A mod PA. That's how we're going to compute it eventually. For every maximal ideal in this ring, the inverse image gives a maximal ideal in A that contains P, and vice versa. Okay? Now, what does it mean to be a product of prime ideals? Well, in general, when you have a commutative ring, you define the product of two ideals, Ij. It's a new ideal, but it's extremely complicated. It's a combination of all alpha I, beta I, where for I equal 1 to n maybe, where alpha I is in I, and beta I is in J. Now you might think, oh, it's just made by the products. But no, because that's not closed under addition. So then you have to take sums of products. It's like tensor product. And so in general, if you're in a ring, you have absolutely no clue what the product of two ideals is. It's an ideal that's closed under addition and multiplication from the ring, but you don't know what it is. But in Dedekind domains, it behaves a little bit better. And the only time you can really say what the product of two ideals is you can say what the product of the principal ideal alpha is by the principal ideal beta. It's alpha beta. Because there, these sums are still in this ideal. But, so first of all, the theorem is that any ideal decomposes uniquely as a product of primes, and that the norm of the ideal, the index of the ideal is the product of the index of the primes. Pi. Well, if you have that theorem of decomposition in the Dedekind domain into prime ideals, then you can rewrite this zeta function in terms of the prime ideals, just as Euler wrote the zeta function of Q in terms of the primes. Namely, the zeta function of K of S, which is by definition the sum over the non-zero ideals, 1 over the norm of I is the S, can also be written as the product over the prime ideals, again not zero, of 1 minus the norm of P to the minus S inverse. Because if you blow this out, you get the terms here for prime powers, and every ideal is uniquely a product of prime powers. So you have this Euler product, again, for the real part of S greater than 1. And that's what's going to allow us to identify these zeta functions in some very simple cases. By figuring out how many primes we have and what their norms are, etc., we'll be able to calculate what this series is and relate that to other functions. So let's, before I do that, I want to do one more invariant of a number field, and then we'll get to computing a few zeta functions so we see how they actually work. And that invariant is the discriminant. You see, if this, remember that A is the direct sum of n algebraic integers. Now there's a quadratic form on this Z module because you have the trace map, which is a linear map from A to Z. It's just the coefficient of the, every element alpha satisfies a characteristic polynomial x to the n minus the trace of alpha. Sorry, this is n. X to the n minus 1 plus or minus the norm of alpha. That's the definition of the norm. Because if you left multiply by alpha on A, you get a Z linear map, and that has a trace, that has a characteristic polynomial. So this is the characteristic polynomial of left multiplication by alpha on A. And that's the definition of the trace of the norm. So the trace is a linear map from A to Z, or a Z linear map. And if you have a pairing, alpha beta, which is the trace of alpha beta. And that's a non-degenerate quadratic form, at least over the rational numbers, because for any element in the field, at least, the trace of alpha times alpha inverse is the trace of 1, which is not 0, it's n. The trace of 1 is n, by this definition. So you can take the Graham matrix of that form and take its determinant, and that's called the discriminant of the number field. So by definition, the discriminant of the number field, discriminant of K, sometimes it's written D or DK, it's really the discriminant of the ring of integers, is the determinant of the n by n symmetric matrix, which is given by alpha I, alpha j. The determinant of the n by n matrix of trace of alpha I, alpha j. Okay, let's work out the ring of integers in quadratic fields and calculate their discriminants and things like that. There are a few cases you can work these things out explicitly. So let's try the case where k is equal to q square root of d. Actually, let's call this maybe e, because I don't want to confuse it with the discriminant, where e is an integer and it's square free. We might as well make it square free if we're taking the square root of it. And so therefore, the ring of integers certainly contains z plus z square root of e. Good. And you might ask, are there any more algebraic integers? Well, it depends on what e is. So e is not divisible by 4, so its residue mod 4 is either 1, 2, or 3. So if e is congruent to either 2 or 3 mod 4, this turns out to be an equality. A is equal to c plus c. But if e is congruent to 1 mod 4, it turns out you can make, it turns out that there's another algebraic integer, alpha, which is 1 plus square root of e over 2 is an algebraic integer. Well, you have to check that it satisfies a quadratic polynomial with integer coefficients, and so the trace of alpha is clearly an integer. It's 1, right? If you add alpha to its conjugate, it's 1. What about the norm of alpha? Well, the norm of alpha is 1 plus e times 1 minus e, so it's 1 minus e squared, I guess, over 4. But that's okay too, because e is congruent to 1 mod 4, so that's also an integer. So it has e and so in this case, A contains this ring with index 2. But again, it's generated by a single element. So this is, in this case, A is z plus z, 1 plus square root of e over 2. Let's compute the discriminant. Since we have the ring of integers and we know how to do traces, we can compute the discriminant. What is the discriminant of A? Well, in this case, where A is that, we have to take the determinant of the matrix of traces. So the basis is 1 and the square root of e. The trace of the square root of e is 0, so that's easy. The trace of 1 is 2, 0, 0. And then we have to take the trace of square root of e times square root of e, which is 2e. You have to take the determinant of that matrix, and you get 4 times e. Okay? Everyone agree with that? Okay. And let's try it in this case, where the basis is 1 and this element. So in this case, the determinant of A, the discriminant of A, is the determinant of the matrix. Well, we still get 1. The trace of that is 2. Then we take 1 times alpha, take the trace of that. So the trace of alpha is 1. We get 1 and 1 here. And then finally, we have to multiply alpha by itself and take the trace. Okay, so what does multiplying alpha by itself give us? So we get 1 plus 2 square root of e plus e over 4, if I got that right. We take the trace, we get e plus 1 over 2. Did I do that right? 1 over 2. Yeah, e is 1 mod 4, so that's okay. I'm a little confused here. The norm is this. E squared, this thing squared, still has to be an algebraic integer. 1 plus 2 squared e plus e over 4 plus 1 over 2. Let's try it. Good. When we take the determinant of that, we get e plus 1 minus 1, which is e. So the discriminant in this case turns out to be e, and the discriminant in these two cases turns out to be 4e. And that's a general phenomenon. The discriminant turns out to be always an integer which is congruent to 0 or 1 mod 4. So e was not congruent necessarily 0 or 1 mod 4. So here to get it to be 0 mod 4, we had to multiply it by 4. And here it is already congruent to 1 mod 4. And if you wanted to write the ring of integers uniformly, just in terms of this discriminant, instead of this square-free integer, which is what people like to do, I prefer to write it in terms of the discriminant. And in terms of the discriminant of the quadratic field, the ring of integers can always be written as this way: z plus z, d plus root d over 2. Because when d is divisible by 4, which is in these two cases, right? This is just 4e. The square root of it is 2 squared e. You divide it by 2 and you get square root of e. And in the other case, it works out well because this thing is odd. Okay. So that's the ring of integers. Now, what about the prime ideals of this quadratic ring? Well, we have a basis for it. We see, and we saw, by the way, that this always contained this z plus z square root of d. In this case, it contains this with index 2, right? Yeah. Right. Contains it with index 2. Okay. So if I want to study the prime ideals of A, I have to study the maximal ideals of the ring A mod PA. And for the prime P, as long as P is not 2, and we're going to leave that aside for the moment, although everything works out beautifully for P equal to 2, I could equally well work with the maximal ideals of this ring, because A mod PA would be the same as the ring Z square root of D mod P for P not equal to 2. I mean, 2 is invertible in this ring, so that's no difference. Okay, so how do I work out the maximal ideals of that ring? Well, I write this ring as z of x modulo x squared minus d, the discriminant, and then I'm trying to divide that by the ideal p. Okay, so if you think of it, I'm taking this ring, I'm first modding out by this ideal, and then I'm modding out by that ideal. So that's the same ring as the ring where I take z of x and I mod out by the ideal generated by p and x squared minus d. And then I can say, well, why did I first mod out by this and then mod out by, why don't I do it the other way around? That's the same as the ideal z mod p z of x. That's what I divide by this prime. And then I divide it by the image of x squared minus d, which is just this polynomial taken mod p. Okay? So this is a quadratic extension of the ring Z mod p. And the ideals in it depend on how this thing factors mod p. That's the general moral of the story. And this works for a general ring of integers. If you find some finite index thing generated by a single element alpha, and alpha satisfies the polynomial f of x equals 0. F of alpha is equal to 0. and then you take a prime that does not divide this finite index. Then the factorization, then if you want to study the ring A mod PA, that's the same as Z of alpha mod P, which is the same as Z of X modulo the ideal generated by f of X and P, which is the same as the ring Z of P, Z mod P of X modulo the image of F, which is just F thought of as mod P. And the maximal ideals of this ring correspond to the irreducible factors of this polynomial. So I have to see how this polynomial behaves mod P. And there are three cases. First case, P divides D. If P divides D, this is just the polynomial x squared, right? So then there are two roots, but they're the same. There's one irreducible factor, x. And so in that case, the ideal P times A is just the square of one ideal of degree 1. And the second case is that x squared minus D is irreducible, mod P. And in that case, this is already a field. So in that case, PA is already a prime ideal. And it's a prime ideal of norm 2. And the third case is x squared minus D looks like x minus alpha times x minus beta. It splits into two distinct roots. And in that case, there are two maximal ideals whose product is P, and they each have degree 1, so norm P. Okay. So that the zeta function, if I took it in this form for this quadratic field, assuming that P is odd, so if I have this, so I have a K of discriminant D, which is, remember, either equal to 4 times the square free thing or the square free thing. And it's always congruent to 0 or 1, not 4. So you can say that the discriminants of quadratic fields are the numbers that are congruent to 0 or 1 mod 4 and are as square free as possible given this condition. Okay, I have that, and I assume that P is not 2, just to be really crude here. Then this product over P of 1 minus norm of P to the minus S inverse can be written as a product over rational primes P of 3 different types. First of all, the primes dividing the discriminant, I just get 1 minus P to the minus S inverse, because there's a unique prime and it has degree 1. So namely, the norm of the ideal PA is clearly P squared, because that's the index of this in the full ring of integers for a quadratic field. Okay? So I get that. And then I get the product of the P where x squared minus D is irreducible of 1 minus P to the minus 2S inverse. Because there's a unique prime dividing the rational prime P, and it has norm P squared. And then finally, I get the product of the primes P where x squared minus D has 2 distinct factors. And you get 1 minus P to the minus S times 1 inverse times 1 minus P to the minus S inverse, because there are 2 different primes and they each have norm P. Okay? Great. Now, here's the big theorem. Well, so that's the zeta function of K. But the theorem of quadratic reciprocity says, so this is the case where D is a square mod P. So D is congruent to a square mod P, but non-zero. And this is the case where D is congruent to is not congruent to a square mod p. And this is the case where d is congruent to 0 mod p. So it depends on the precise Euler factor in the zeta function depends on how d behaves mod p. But the theorem of quadratic reciprocity tells you that whether d is a square mod p or not depends only on what p is mod d. So the factorization of PA depends only on P mod the discriminant D. Not on D mod P, but on P mod D. And let's see how it looks in a simple case. So let's do the quadratic fields of prime discriminant. Okay, of prime discriminant. Well, then if it's a prime discriminant, it has to be congruent to 1 mod 4. It's not going to be congruent to 0 mod 4. So you either have D is equal to L, congruent to 1 mod 4, or D is equal to minus L, where L is congruent to 3 mod 4. So they're all congruent to 1 mod 4. So for a prime which is 1 mod 4, you can make a quadratic field that's discriminant L. And for a prime congruent to 3 mod 4, you can make a quadratic field that's discriminant minus L, just by taking E to be L or minus L, congruent to 1 mod 4. Okay? Now, so we want to know when is L or minus L, depending on what L is mod 4, a square mod P. So that's the question is LP, what is LP equal to? Well, if L is 1 mod 4, then in this case, this is the same as PL, right? And if L is 3 mod 4, then we have minus L here, and that's also the same as PL by quadratic reciprocity. So this plus or minus, well, sorry, let me just say D mod P turns out to be just P mod, the quadratic symbol of P mod L. I mean, in all cases. And if you think about this, this is a quadratic character, but P goes to PL, extends to a quadratic character chi from Z mod L star to plus or minus 1. Namely, this symbol, if I now take an arbitrary element mod L and I write it as a product of primes, and I take the product of these things, that gives me a quadratic character of the integers mod L. Or you can write this as the same thing as Z mod D star. So in other words, this condition that D is not a square mod P, in the case at least where the discriminant is a prime, is the condition that chi L of P is equal to minus 1, that P is not a square mod L. And this is the condition that chi L of P is equal to plus 1. So it's very subtle. I mean, the completely naive way of determining primes just says take the polynomial and factor it mod P. But this says that the factorization of this specific polynomial, x squared minus L mod P, has to do with what P is mod L and is determined by a character mod L, a Dirichlet character mod L of order 2. And so now we can rewrite this. And that's what Dirichlet did. He took the theorem of quadratic reciprocity out of Gauss's work and turned it into this analytic statement. Because look, we get the product of P dividing D, we don't do anything with that, 1 minus P minus S, inverse. And then we get the product of P where chi L of P is equal to minus 1 of, well, this thing can be written as 1 minus p to the minus s times inverse times 1 minus chi L of p times p to the minus s inverse. Because this would be a minus 1, so this would be a plus, and when you multiply those two terms, you get this. And the final one would be the product of p, where chi L of p was equal to plus 1, and there we get the same thing, 1 minus p to the minus s inverse. And then instead of writing it like this, I'd write 1 minus chi L of p to the minus s inverse. Okay? And then I'd regroup terms, and I'd realize that for every prime p, I have this term, and that's the Euler factor in the zeta function. And then the rest of the terms, I don't get anything for p dividing p, but for the other primes, I get the Euler factor of the Dirichlet L function. And so this becomes the same as the product of zeta s, L chi L of s, where chi L is this quadratic character of the integers on L star. And Dirichlet checked that quadratic reciprocity worked in all cases. That the quadratic symbol of D depends only on chi of p for a character chi from z mod d star to plus or minus 1, and that Dirichlet L function gave the zeta function of k. So in that case, this generalization of the zeta function and this generalization are related by quadratic reciprocity. Okay, let's not stop there. Let's do the product of the L functions that we were looking at when we were trying to prove that the L functions didn't have a 0 at 1. Namely, let's fix a prime L. Fix L. And let's do the product over all chi of z mod L z star, all chi L chi s. Okay, in fact, why are we doing just an L? Well, let's do a D. Fixed an M, sorry, let's do an M. So all chi of this, we found that had an Euler product that looked like this. The product over all primes P of 1 minus P to the minus Fs to the phi of M over F, where F was equal to the order of P in Z mod MZ star. And if we instead of, C not dividing M. Okay, now what we really should, good. Remember this? This was our reorganization of this product. Okay, now I'm going to take the case where M is a prime again, just to make life simple. Prime. Okay, and I claim that this product is the zeta function of the cyclotomic field generated by the L fruits of unity, which was a field that was studied extensively by Coleman. Okay, so we have to see why that's the zeta function of that field. And in general, it's the zeta function of the nth cyclotomic field. It's a little easier for me to do the prime case. Okay, what is the ring of integers in this? So what is this cyclotomic field? Well, to adjoin it's the same thing as adjoining a primitive L root of unity, namely not 1, which is a root of the polynomial f of x is x to the L minus 1 over x minus 1. In general, you have to take away all the roots of unity in order to finding M. And that's a polynomial with integer coefficients, which Eisenstein proved was irreducible. Gauss had also proved it's irreducible. So you get an extension of degree L minus 1 over the rationals. And Kummer was extremely lucky because in this case, it turns out that the ring of integers is exactly the ring generated by a root of unity. This lucky accident is probably responsible for algebraic number theory because he just worked with that ring. And that ring has all the nice properties of the ring of integers because it turns out to be the ring of integers. And in fact, you can prove that it's discriminant. This is a good exercise, see if you like to do this kind of exercise. Its discriminant is minus 1 to the L minus 1 over 2 times L to the L minus 2 power. You can check that that's a number which is congruent to 1 minus 4. Okay, so that's the ring of integers, that's its discriminant, etc. How do primes factor in this? Well, we have to study the factorization of that mod p. Right? If we have a generator of the ring of integers, we just have to see how it factors mod p. Let's see if I can do this properly. All right, well, let's let, well, look, if L divides, if p is equal to L, the factorization of this is just x modulo p, this is x minus 1 to the Lth power, so the polynomial f tilde is just x minus 1 to the L minus first power, so p times the ring of integers is just a prime of degree 1 to the L minus first power, and all we do is get one power of p in the zeta function. Okay, so we'll assume p is not L, and let f be the order of p in Z mod L star. So what that means is that p to the f minus 1 is divisible by L, but no smaller power of p minus 1 is divisible by L. Okay? Which means that if you take the field of p elements and you adjoin to it a primitive Lth root of unity, then you get the field of p to the f elements. Because the multiplicative group of this field has order p to the f minus 1, and that contains an element of order L, namely an Lth root of unity, right? But no smaller field could contain an Lth root of unity because no smaller power of p has the property that p to the f minus 1 is divisible by L. Okay, so therefore there are homomorphisms from the ring of integers to this finite field by taking z to z mod p here and taking the Lth root of unity to this Lth root of unity. So that's it. So the prime ideals there are homomorphisms from A to this f p to the f, which is fp ul. There are ring homomorphisms. And so there are prime ideals, which are the kernels of that memory. How many ring homomorphisms are there? Well, let's see what I got here. Getting there, but slowly but surely. Yeah, there are L minus 1 ways. There are L minus 1 ways to map A to this, namely because this is Z zeta. So you can take zeta to any non-trivial Lth root of unity in that field. Right? And that determines the homomorphism because Z goes to Fp. That's given. And how many give you different prime ideals of A? Well, you have to look at the kernel. And if you look at the automorphism group of this over Fp, that's a cyclic group of order F. And that permutes the different Lth roots of unities around in some way. And the kernel of the map would be exactly the same if you first took a homomorphism and then applied an automorphism here. Right? So there are L minus 1 over F, different kernels. And each kernel is an ideal PI, where the norm of PI is equal to P to the F, because that's the size of the quotient field, correct? So we now know how P factors in this ring of cyclotomic fields, namely the ideal PA looks like the product from I equal 1 to L minus 1 over F of PI, and each one of these things has norm P to the F, because I've determined the different prime ideals containing P. Okay, well look at this. This is perfect. Namely, I have 1 minus the norm of the ideal to the minus S power, because P to the F is the norm of the ideal, and I have it this many times. Right? So that's the zeta. So I've just written down this product that I had rearranged before is just the zeta function of the cyclotomic field. And you have to be a little careful because when you get the trivial character here, I didn't have the factor in P, and if I really want the factor at the prime L, which is just this, I want to put the real zeta function in, just like I did in the quadratic case. But essentially, this product turns out to be the zeta function of Q mu L, and that's why it has a pole at S equal 1, because all these zeta functions are going to have a pole at S equal 1, and since this thing ends up with a pole at S equal 1, and we know it contains the zeta function, all the other L functions have to be regular and non-zero at S equal 1. So if you can determine the prime ideals and whatnot, then you can sometimes work out the zeta function in terms of. Now it turns out, and this is a big theorem in the late 19th century, that this works for every field which is an abelian extension of the rational numbers. So if you have a field, K, which is not only Galois over Q, but the Galois group is an abelian group, then an important theorem of Kronecker and then Weber is that it's contained in a cyclotomic field. There's some mth root of unities that contain K. The Galois group of this field is known to be Z mod M Z star. That's another appearance of this Gauss's group. Because if you have an automorphism of the mth roots of unity, it takes a primitive nth root of unity to some other primitive nth root of unity, and that takes zeta to the A, where A is some element mod M, which is invertible, and that determines the automorphism completely. So you get a Galois group of this, and so if you have an abelian group, it's a quotient of this group, and let's call this subgroup H. So by the Kronecker-Weber theorem, an abelian field is contained in a cyclotomic field, and so it corresponds to a subgroup of this group for some m. Okay, and then it turns out, theorem, and that's the generalization of this, what we did for quadratic fields. The zeta function of K, S, is the product of the characters of Z mod M star, whose restriction to H is trivial. In other words, the characters of this finite quotient group of L chi S. So in the case of abelian extensions, the zeta function can always be written as product of Dirichlet L series. In the case of cyclotomic fields, H is trivial, and you use all the characters. In the case, and that's a good case to bear in mind, of a quadratic field, that can be put in a cyclotomic field, and these turn out to be the kernel of a quadratic character. This subgroup is a kernel of a quadratic character, Z mod M star to plus or minus 1. And so you only get the characters that are trivial on that kernel, and there are only two characters that are trivial on that kernel. This character and the trivial character. And that gives the zeta function of this field. So a big question which is motivated late 20th century number theory, and which is still quite open today, is there a similar decomposition for the zeta functions of an arbitrary number field, not necessarily abelian, where these things are replaced by more complicated objects? Okay, and we're going to get into that. But already for cubic fields, for a field of degree 3 over the rational numbers, you can't write its zeta function in terms of these Dirichlet L functions. Okay, now I mentioned the pole of the zeta function, and there's a beautiful formula for the residue of this pole at s equal 1, which generalizes Euler's formula for the regular zeta function. So to do that, I have to tell you about some other invariants of number fields. So we have the discriminant, but I also have to tell you about the class number and the regulator. Another very good paper project for people interested in finding a paper project is to prove this theorem about abelian fields, to prove the Kronecker-Weber theorem that it's contained in a cyclotomic field. There's a lot of treatments of that in the literature, and I'd like you to go a little further, and not only is it contained in the cyclotomic field, but then show that the zeta function of the abelian field is given in terms of the Dirichlet characters that vanish on that subgroup. Okay, so let's do the, let's see how much time, oh good, I have to do it. Not much. So I'll do the class group, and then maybe we'll do the regulator later. So as I said, if you take the ideal group, the group, what are usually called fractional ideals, so you have inverses, ideals in K, that's a very simple group. That's a direct sum over the prime ideals P of a copy of Z for each prime ideal P. Because any fractional ideal is given by a product of, any fractional ideal is the product of PI to the AI, where these are integers, now not necessarily positive integers, and almost all of them are 0, because it only involves a finite number of primes, so it gives you an element in this group. And conversely, any element in this group gives an ideal. So this is just a free abelian group on these generators with the prime ideals. Okay. And as I mentioned, not every ideal is necessarily principal. So you have a subgroup of the ideal group, the ideals which are generated by one element. Ideal group. And the quotient group is called the ideal class group. And the fundamental theorem in algebraic number fields is that the quotient group is a finite group, the class group, and its order is usually denoted H. And you get very quickly to fields which have non-trivial class groups. So for example, if you look at the imaginary quadratic discriminants, imaginary means negative, so D less than 0. So remember, it has to be congruent to 0 or 1 mod 4, and it has to be as square free as possible. So I'll give you a list of them. The first one is -3, that's congruent to 1 mod 4. Then -4, that's the discriminant of the Gaussian integers. This is the discriminant of the third roots of unity, which is the quadratic. And then you get -7, -8, and then you get -11. If you get to -12, that's okay, that's divisible by 4, but it's not as square free as possible because you can divide it by 4 and get a discriminant, namely -3. So that's not a discriminant. And then you get -15, and likewise -16 is 4 times -4, so that doesn't count. And then you get -19 and -20. That works because you can't divide it by 4 and get something congruent to 0 or 1 mod 4. You get -5, -23, etc. Okay, the class numbers are 1 up to this point. But they're no longer 1 necessarily. So this has class number 2. And this has class number 1. It turns out that's class number 1. And this, which is the same thing as square root of -5, that's the famous, that was the first case where they found it was not a principal ideal domain. This has class number 3. And Gauss made extensive computations in class numbers. He had a different way of doing it, and speculated that each class number occurred only finitely many times. We now know that that's the case. So that's the first invariant of a number field, the class number, or if you wanted more information, the structure of this finite abelian group. There's a lot of evidence, not only that the class number goes to infinity for imaginary quadratic fields, but these conjectures of Kohn and Lenstra say basically that the class group is an arbitrary, is a random finite abelian group. So, for example, that says that if you had, if 9 exactly divides the class number, and you say, well, what do I have inside the class group? Do I have z mod 3 squared, or do I have a z mod 9? It turns out that this is much more likely than this from a probabilistic point of view, and that's what one finds. It's harder to make class groups of this sort than this sort. Anyhow, that's another great project. If people want to do something on the class group, they could do the Kohn-Lenstra heuristics, which is a very hot topic nowadays. Okay. And finally, I want to just tell you what the unit group is, and next time we'll do the regulator. So the principal ideals also fit into an exact sequence. Namely, they're quotients of the multiplicative group of the field. Namely, you take alpha and you take it to the principal ideal, alpha A. That's a fractional ideal, right? And when do you get the trivial principal ideal? Namely, when do you get the ideal A? Well, precisely when alpha is a unit and be inverted in the ring of integers, right? And that's a subgroup of the multiplicative group of the field, which is the unit group of the ring of algebraic integers. They're called the units. So the units in the class group are the two cool invariants of a number field, and this is known to be finite. The units are not always finite, although they are in this case. In this case, they're finite, but the units are known to be finitely generated. And the rank is R1 plus R2 minus 1, where R1 and R2 are the number of real and complex embeddings of the field. So if you have embeddings into the reals, there are one of those. So they have to do with the factorization of the polynomial f of x over the real numbers. This is the number of real roots, and this is the number of pairs of complex conjugate roots. So I'll start next time with how you prove the unit theorem and define the regulator, and then we'll be in position to say at least what the residue of this is at s equal 1. Okay? Good. And then, finally, we're going to go back and do exactly how Dirichlet did this, because Dirichlet didn't have the ring of integers, and he didn't have prime ideals, and he didn't have units and class groups or anything. He had nothing but Gauss's theorem of binary quadratic forms. But he was able to do the zeta function in quadratic fields in terms of binary quadratic forms, which is very instructive, and I'll show you how he did that too. There's a good number theory talk today for those people interested. Conway is visiting from University of Arizona, and he's giving a pre-talk now, 120 for graduate students, which I highly recommend, and then the talk is at 2. He's a good speaker, and you'll learn a lot. I did my advertising.
I would say it's safe to go over it again, especially because there may be people sitting that either haven't had a formal class.